Hello and welcome to this chemistry video on gas properties and behavior. So the first thing we want to do is just kind of get a background about the kinetic molecular theory and how it relates to gases. So kinetic molecular theory is about how molecules are moving, and so we have that gases consist of very large numbers of tiny particles that are very far apart. In other words, they have very low density. Gas particles are in constant rapid motion in random directions, and when they are colliding either with each other or with their container, we consider those collisions to be elastic. There are no forces of attraction or repulsion between those gas particles, or we make that assumption, and then the kinetic energy of the gas particles is temperature dependent. Okay, and so those are some principles that really guide some of our understandings about gas molecules. So then we want to know about how gas particles will move. And so we have two big ideas here. Diffusion is how gases move from a high concentration to a low concentration. They basically fill out that space that they're in. And then effusion is how gas particles will actually escape through tiny openings or pores or holes in their container. And the really, really big idea here, which might be a little tough to see, there we go, is that smaller molecules move faster than larger molecules. And in particular, when we're looking at this, a lot of times we'll evaluate this based on molar mass. Okay, so lower molar mass. So a lot of times that size is going to be based on molar mass. All right. So gas temperature itself, we need to know a few things. Oh, my stuff didn't transfer over here. So kinetic energy of gas particles is temperature dependent, and we use the Kelvin scale, which really is about particle motion. Is that scale? There's more to the actual foundations of that, but we know that we can convert between these, and so we know that to find Kelvin, and we are going to want to find Kelvin, it is going to be degrees Celsius plus 273. We'll just round that to 273. It works just fine. And if we wanted to convert back to degrees Celsius, it's going to be Kelvin minus 273. And so we can use those to work back and forth between those units. In this diagram, what we want to do is we want to take a look at these pressure units that we have. So if we have kilopascals, which is kPa, lowercase k, big P, little a, so that's kilopascals. We can move between kilopascals atmospheres, ATM, which are atmospheres, and millimeters of mercury. Millimeters of Hg, okay, so millimeters of mercury, by just doing some simple conversions. And so we know there's 101.3 kilopascals is equal to 760 millimeters of mercury. 1 atmosphere is equal to 101.3 kilopascals, and then 1 atmosphere is also equal to 760 millimeters of mercury. And so we can use this to do some conversions. So let's do a couple of those. So the first one, what is the pressure of 3.2 atmospheres of gas? So we're going to start with 3.2 atmospheres on the top because that's the data value we're given, and we want to know what this would be in millimeters of mercury. So our conversion factor, we said for every 1 atmosphere, there is 760 millimeters of mercury. Okay, so we're just going to divide 3.2, going to multiply 3.2 times 760, and we get 2,400 millimeters of mercury with significant digits. If we want to go back we want to go a different direction, we can start with our 115 kilopascals, okay, and we want to know atmospheres. So 115 kPa, there are 101.3 kPa for every 1 atmosphere. So 115 divided by 101.3, and I get 1.14 with significant digits, 1.14 atmospheres. So just some simple conversions. Sometimes it's nice for us to go back and forth between them. There are times where we will see some standard values, and sometimes the difference between that is the pressure units that we are in. In addition to that, we have gas mixtures, and gas mixtures are multiple gases, and it follows along with those same principles of kinetic molecular theory. And so we know that these can be together, but the partial pressure of each gas in this mixture is additive to find the total pressure. And so we have this equation, P total is equal to all of the partial pressure. So P1 would be like the partial pressure of oxygen. So we could say this one is oxygen, and this one could be nitrogen if we were looking at this particular example, okay? And then we wouldn't have additional ones. But we could have more than that depending upon what we have for values. So let's work a problem here. What is the pressure of O2? So this time we don't want to know total pressure, we want to know a partial pressure for O2 in a gas mixture with a total pressure of 30 atmospheres. And we also have, in addition to oxygen, carbon dioxide and nitrogen. So let's just write out the overall equation first. So P total is going to be the pressure from O2 plus the pressure from CO2 plus the pressure from N2. Okay. Now, we know all of them except for the pressure of O2. So this is what we want to solve for. Okay, so we can plug all of our other numbers in. We have a total pressure of 30.0 atmospheres, and that's equal to PO2 plus 9.6 atmospheres for carbon dioxide plus 14.4 atmospheres for nitrogen. And so the pressure of O2 is going to be 30 minus 9.6 plus 14.4. I'm going to put those in parentheses together. So let's go ahead and do that in my calculator. 30 minus 9.6 plus 14.4 in parentheses. And I get a total of 6. We want to make sure that we have one significant digit since we're adding and subtracting, one place value right of the decimal. So that's going to be 6.0 atmospheres, and that would be our answer. I hope this was helpful, and we will do some additional practice in class.